Okay, in this video, we're just going to quickly solve that last example we did by hand for the Brayton cycle, and we'll use this thermofluid site, the TEST site, if this is something that you use. So I'll go ahead and show you how to do it. So we'll go ahead and set it up. So let's go ahead and get our correct test app here. So this is going to be a steady state Brayton system. So we've got an open system, steady state, and this is actually a very specific one, which would be a gas power cycle. We'll go ahead and do a single gas with a constant heat capacity. So that's going to be that perfect gas model. So we'll go over here and open up our window. And remember, we've got, if we come back to what our system looks like, we got 4 states. 1 to 2 is our compressor, 2 to 3 is a heat addition, 3 to 4 is a turbine, and then 4 to 1 is the exhaust. So let's go ahead and define those states. So state 1 is going to be the inlet, and our pressure was 100, and the inlet temperature was in degrees Celsius, and that was 27. It can calculate all the intensive variables. Let's go ahead and just do this per mass like the last one did. So we'll go ahead and just send our mass flow rate to 1, and then we can get our extensive variables as well. So state 2 is going to be at the end of the compressor. So that was actually at 2 megapascals or 2000 kPa. It was isentropic initially, so that would just be equal to S1. And then we'll go ahead and keep our mass flow rate constant through the whole thing. So I'll just keep calling this M.1 to go ahead and grab it from the first one. And there we go. Now we've got our heat addition, and the pressure is not going to be that high pressure. It'll just be P2. I could also put 2000 in there. This went up to not degrees Fahrenheit, degrees Celsius, up to 727. Again, keeping our mass flow rate constant. And we go to state 3. Now we'll go to our last state, and the pressure will go back to our initial pressure, which is equal to P1. And that was isentropic, so that's going to be equal to S3. Again, keeping our mass flow rate constant. M.1. And okay, so then if we look at it, here we go, 1 to 2, straight up, 3 to 4, this is a TS diagram, looks correct. So now we need to go ahead and connect it. So we'll go to the device panel, and so our first device is just, we're going to connect 1 to 2, and then 2 to 3, 3 to 4, etc. So I'll go ahead and start with 1, connect that to 2, and then the next device will just go 2, connecting to 3, and then keep moving through here, 3, going to 4, and then our final device is state 4, returning to state 1. Now let's go ahead and in device 1, originally this was our compressor, so this was there was no heat addition to it, so that was going to be isothermal, or sorry, it's going to adiabatic. So we'll go ahead and there's the work requirement. It's a minus because it doesn't generating work, it's the work requirement. This was our heater, so there was no work in that one. So this is the amount of heat being entered. And then again, this would be adiabatic. And then our last device was, there's no work in that one. So now we've got it. And if we come back here and look at our cycle panel, it actually computes our complete cycle. There's our efficiency of 57.5%. So we did that with the isentropic. Now let's look how we do that, the isentropic efficiency of the compressor. So come back over here, 1 to 2. What's changing now is actually we're going a little over here with this 90% efficiency. Now, one thing you can't do a test is call a state 2A or 2B or 2S or something like that. They all need to have just regular numbers. So we're going to go ahead and call that state 5. So we're going to go 1 to 5, and then we'll go ahead and 2 will be the hypothetical state. And we'll use that compressor efficiency equation. So the compressor efficiency would be 2 over 1, the enthalpy over 5 over 1, right? It's going to be a number less than 1. I'm going to rearrange it because I want to know what H5 is in terms of 2. So here's my equation. H5 is H1 and then 2 minus 1 over efficiency. So we'll go ahead and put that into test. So we're going to come over here, and we're going to add another cycle, or sorry, not another cycle. We're going to add another state. So we're going to go ahead and this will be state 5. So this is going to be state 5, and this is actually going to be this essentially state 2. So it's going to be at pressure 2. But now instead of making it isentropic, we're going to define H5 from that equation I had before, which was H1 plus H2 minus H1 divided by 0.9. Keeping that mass flow rate the constant, equal M.1. And let's go ahead and check that. And 752 is at temperature at T5. And if it was isentropic, it was 706, so it sounds like it's right. So now what we need to do, here's our 0.5. It looks like it's up and to the right like we'd expect, but now we need to connect our device. And so come over here, back to device 1. 1 is not going 1 to 2, it's actually now going 1 to 5. And then the next device is going 5 to 3. So that's what we want to go ahead and do. And so then if we calculate all of that and come back to our cycle, we see this 49.8, or essentially 50%, which is what we saw in our previous example. So, okay, that's how you do it if you're using this site.